This is the Large Hadron Collider. It's 27 kilometers in circumference. It's the biggest scientific experiment ever attempted. Over 10,000 physicists and engineers from 85 countries around the world have come together over several decades to build this machine. What we do is we accelerate protons, so hydrogen nuclei, around at 99.999999% the speed of light. Right, at that speed, they go around that 27 kilometers 11,000 times a second. And we collide them with another beam of protons going in the opposite direction. We collide them inside giant detectors. They're essentially digital cameras. And this is the one that I work on, Atlas. You get some sense of the size. You can just see these EU standard size people underneath. You get some sense of the size. 44 meters wide, 22 meters in diameter, 7,000 tons. And we recreate the conditions that were present less than a billionth of a second after the universe began, up to 600 million times a second inside that detector. Immense numbers. And if you see those metal bits there, those are huge magnets that bend electrically charged particles so we can measure how fast they're traveling. This is a picture about a year ago. Those magnets are in there, and again, an EU standard size real person, so you get some sense of the scale. And it's in there those mini Big Bangs will be created sometime in the summer this year. And actually this morning I got an email saying that we've just finished today building the last piece of Atlas. So as of today, it's finished. I'd like to say that I planned that for TED, but I didn't. So it's been completed as of today. Yeah, it's a wonderful achievement. So you might be asking, why? Why create the conditions that were present less than a billionth of a second after the universe began? Well, particle physicists are nothing if not ambitious. And the aim of particle physics is to understand what everything's made of and how everything sticks together. And by everything, I mean, of course, me and you, the Earth, the Sun, the 100 billion suns in our galaxy, and the 100 billion galaxies in the observable universe. Absolutely everything. And you might say, well, okay, but why not just look at it? If you want to know what I'm made of, let's look at me. Well, we found that as you look back in time, the universe gets hotter and hotter, denser and denser, and simpler and simpler. Now, there's no real reason that I'm aware of for that, but that seems to be the case. So way back in the early times of the universe, we believe it was very simple and understandable. All this complexity, all the way to these wonderful things, human brains, are a property of an old and cold and complicated universe. Back at the start, in the first billionth of a second, we believe, or we've observed, it was very simple. It's almost like, imagine a snowflake in your hand, and you look at it, and it's an incredibly complicated, beautiful object, but as you heat it up, it'll melt into a pool of water, and you would be able to see that actually it was just made of H2O, water. It's in that same sense that we look back in time to understand what the universe is made of. And as of today, it's made of these things, just 12 particles of matter stuck together by 4 forces of nature. The quarks, these pink things, are the things that make up protons and neutrons, that make up the atomic nuclei in your body. The electron, the thing that goes around the atomic nucleus, held around in orbit, by the way, by the electromagnetic force that's carried by this thing, the photon. The quarks are stuck together by other things called gluons. And these guys here, the weak nuclear force, probably the least familiar, but without it, the sun wouldn't shine. And when the sun shines, you get copious quantities of these things called neutrinos pouring out. Actually, if you just look at your thumbnail, about a square centimetre, there are something like 60 billion neutrinos per second from the sun passing through every square centimetre of your body. But you don't feel them, because the weak force is correctly named. Very short range and very weak, so they just fly through you. And these particles have been discovered over the last century, pretty much. The first one, the electron, was discovered in 1897. And the last one, this thing called the tau neutrino, in the year 2000, actually, I was going to say just up the road in Chicago. I know it's a big country, America, isn't it? But just up the road. Relative to the universe, it's just up the road. So this thing was discovered in the year 2000, so it's a relatively recent picture. One of the wonderful things, actually, I find, is that we've discovered any of them when you realize how tiny they are. You know, the step in size from the entire observable universe, so 100 billion galaxies, 13.7 billion light years away, the step in size from that to Monterey, actually, is about the same as from Monterey to these things. Absolutely exquisitely minute, and yet we've discovered pretty much the full set. So, one of my most illustrious forebears at Manchester University, Ernest Rutherford, the discoverer of the atomic nucleus, once said, all science is either physics or stamp collecting. Now, I don't think he meant to insult the rest of science, although he was from New Zealand, so it's possible. But what he meant was that what we've done really is stamp collect there. Okay, we've discovered the particles, but unless you understand the underlying reason for that pattern, you know, why it's built the way it is, really you've done stamp collecting, you haven't done science. Fortunately, we have probably one of the greatest scientific achievements of the 20th century that underpins that pattern. It's the Newton's laws, if you want, of particle physics. It's called the Standard Model, beautifully simple mathematical equation. You can stick it on the front of a T-shirt, which is always the sign of elegance. This is it. I've been a little disingenuous because I've expanded it out in all its gory detail. This equation, though, allows you to calculate everything other than gravity that happens in the universe. So you want to know why the sky is blue, why atomic nuclei stick together. In principle, if you had a big enough computer, why DNA is the shape it is. In principle, you should be able to calculate it from that equation. But there's a problem. Can anyone see what it is? A bottle of champagne for anyone that tells me. I'll make it easier, actually, by blowing one of the lines up. Basically, each of these terms refer to some of the particles. So those W's there refer to the W's and how they stick together, these carriers of the weak force. The Z's the same. But there's an extra symbol in this equation, H. Right, H. H stands for Higgs particle. Higgs particles have not been discovered, but they're necessary. They're necessary to make that mathematics work. So all the exquisitely detailed calculations we can do with that wonderful equation wouldn't be possible without an extra bit. So it's a prediction of a new particle. What does it do? Well, we had a long time to come up with good analogies, and back in the 1980s, when we wanted the money for the LHC from the UK government, Margaret Thatcher at the time said, if you guys can explain in language a politician can understand what the hell it is that you're doing, you can have the money. I want to know what this Higgs particle does. And we came up with this analogy and it seemed to work. What the Higgs does is it gives mass to the fundamental particles. And the picture is that the whole universe, and that doesn't mean just space, it means me as well and inside you, the whole universe is full of something called a Higgs field, Higgs particles, if you will. The analogy is that these people in a room, the Higgs particles. Now, when a particle moves through the universe, it can interact with these Higgs particles. But imagine someone who's not very popular moves through the room. Then everyone ignores them. They can just pass through the room very quickly, essentially at the speed of light. They're massless. And imagine someone incredibly important and popular and intelligent walks into the room. They're surrounded by people and their passage through the room is impeded. It's almost like they get heavy, they get massive. And that's exactly the way the Higgs mechanism works. The picture is that the electrons and the quarks in your body and in the universe that we see around us are heavy, in a sense, are massive, because they're surrounded by Higgs particles. They're interacting with the Higgs field. If that picture's true, then we have to discover those Higgs particles at the LHC. If it's not true, because it's quite a convoluted mechanism, although it's the simplest we've been able to think of, then whatever does the job of the Higgs particles, we know have to turn up at the LHC. So that's one of the prime reasons we built this giant machine. I'm glad you recognise Margaret Thatcher, actually. I thought about making it more culturally relevant. But anyway. So that's one thing. That's essentially a guarantee about what the LHC will find. There are many other things. You've heard many of the big problems in particle physics. One of them you heard about dark matter, dark energy. There's another issue, which is that the forces of nature, it's quite beautiful actually, seem, as you go back in time, they seem to change in strength, well they do change in strength. So the electromagnetic force, the force that holds us together, gets stronger as you go to higher temperatures. The strong force, the strong nuclear force, sticks nuclei together, gets weaker. And what you see in the standard model, you can calculate how these change, is the forces, the three forces other than gravity, almost seem to come together at one point. It's almost as if there was one beautiful kind of super force back at the beginning of time, but they just miss. Now, there's a theory called supersymmetry, which doubles the number of particles in the standard model, which at first sight doesn't sound like a simplification. But actually, with this theory, we find that the forces of nature do seem to unify together back at the Big Bang. Absolutely beautiful property. The model wasn't built to do that, but it seems to do it. Also, those supersymmetric particles are very strong candidates for the dark matter. So a very compelling theory. That's really mainstream physics. And if I were to put money on it, I would put money on, in a very unscientific way, that these things would also crop up at the LHC. Many other things that the LHC could discover. But in the last few minutes, I just want to give you a different perspective of what I think what particle physics really means to me, particle physics and cosmology. And that's that I think it's given us a wonderful narrative, almost a creation story, if you'd like, about the universe from modern science over the last few decades. And I'd say that it deserves, in the spirit of Wade Davis's talk, to be at least put up there with these wonderful creation stories of the peoples, the high Andes and of the frozen north. This is a creation story, I think, equally as wonderful. The story goes like this. We know that the universe began 13.7 billion years ago in an immensely hot, dense state, much smaller than a single atom. It began to expand about 1,000,000 billionth of a second. I think I got that right. After the Big Bang, gravity separated away from the other forces. The universe then underwent an exponential expansion called inflation. In about the first billionth of a second or so, the Higgs field kicked in, and the quarks and the gluons and the electrons that make us up got mass. The universe continued to expand and cool. After about a few minutes, there was hydrogen and helium in the universe. That's all. The universe was about 75% hydrogen, 25% helium. It still is today. It continued to expand. About 300 million years, then light began to travel through the universe. It was big enough to be transparent to light, and that's what we see in the cosmic microwave background that George Smoot described as looking at the face of God. After about 400 million years, the first stars formed, and that hydrogen, that helium, then began to cook into the heavier elements. So the elements of life, carbon and oxygen and iron, all the elements that we need to make us up were cooked in those first generation of stars, which then run out of fuel, exploded through those elements back into the universe. They then recollapsed into another generation of stars and planets. And on some of those planets, the oxygen, which had been created in that first generation of stars, could fuse with hydrogen to form water, liquid water on the surface. On at least one, and maybe only one of those planets, primitive life evolved, which evolved over millions of years into things that walked upright and left footprints about 3.5 million years ago in the mudflats of Tanzania, and eventually left a footprint on another world, and built this civilization, this wonderful picture. They turned the darkness into night, and you could see the civilization from space. As one of my great heroes, Carl Sagan, said, these are the things. And actually, not only these, but I was looking around, these are the things, right? Saturn V rockets and Sputnik and DNA and literature and science. These are the things that hydrogen atoms do when given 13.7 billion years. Absolutely remarkable. And the laws of physics, right? So the right laws of physics, they're beautifully balanced. If the weak force had been a little bit different, then carbon and oxygen wouldn't be stable inside the hearts of stars, and there would be none of that in the universe. And I think that's a wonderful and significant story. 50 years ago, I couldn't have told that story because we didn't know it. It makes me really feel that civilization, which, as I say, as if you believe the scientific creation story, has emerged purely as a result of the laws of physics and a few hydrogen atoms, then I think, to me anyway, it makes me feel incredibly valuable. So that's the LHC. The LHC is certainly, when it turns on in summer, going to write the next chapter of that book. And I'm certainly looking forward with immense excitement to it being turned on. Thanks.